Welcome back to RefineryPro. I'm your host, Manoj Kumar, and this is second part of episode 2 on the classification of refractory materials. In the first part of this episode, we explored the different types of shaped refractories. Today, we'll continue by looking at other classifications, starting with refractories based on their physical form, such as unshaped refractories and more. Whether you are an engineer planning a new project or maintaining existing equipment, knowing these classifications is essential for selecting the right material. So, let's dive in and begin exploring the next set of refractory classifications. Now, let's move on to unshaped refractories, which take a completely different approach compared to traditional shaped bricks. Unlike bricks that are manufactured into fixed shapes, unshaped refractory materials are supplied as mixtures of aggregates and binders. They are ready for use either as received or after adding a suitable liquid, usually water. These materials can be dense, for high-strength applications, or insulating, for thermal efficiency, making them extremely versatile. The biggest advantage of unshaped refractories is their flexibility during installation. Because they are shaped on-site, they can easily adapt to complex geometries, tight corners, irregular surfaces, and areas where bricks simply can't fit. How are unshaped refractories installed? Unshaped refractories can be applied using a variety of methods, depending on the material and application. Pouring or self-flowing for castables. Troweling, which is manual application using tools. Vibrating or roughing to remove air pockets. Tamping or pounding to ensure proper compaction. Once installed, these materials harden either at room temperature through chemical bonding or during subsequent heating inside the furnace. Unshaped refractories mainly include castable refractories poured into place and hardened chemically or by heat, moldable materials manually shaped and compacted, similar to clay. Both types provide excellent performance while offering speed, adaptability, and ease of repair compared to shaped refractories. In summary, unshaped refractories offer unmatched flexibility, making them ideal for modern refractory linings where complex shapes, faster installation, and seamless joints are required. Unshaped refractory materials are broadly classified into three main categories. Each category has its own application method, advantages, and typical use cases. The first and most widely used category is castable refractories. These materials are installed by pouring or vibrating them into position, much like concrete. Once placed, they harden either through chemical bonding or during heat exposure inside the furnace. The biggest advantage of castables is their ability to provide excellent surface coverage, fill complex and irregular shapes, create joint-free linings for better structural strength. This makes castables the most popular choice in modern refractory applications. The second category is moldable refractory materials, or simply moldables. These are usually supplied in a moist, ready-to-use condition, or they can be moistened on-site to achieve the required workability. Because they are shaped by hand, moldables are ideal for repairs, small sections, and complex areas where precise manual control is needed. The third category is plastic ramming mixes. These materials are compacted using manual or pneumatic rammers. The ramming action helps achieve high density, strong particle bonding, excellent mechanical strength after installation. Plastic ramming mixes are commonly used where durability and abrasion resistance are critical. Each of these three unshaped refractory types serves a different purpose. The selection depends on the application conditions, the geometry of the lining area, the performance requirements such as strength, thermal resistance, and installation speed. Now that we understand the classification, let's move ahead and take a deeper look at castable refractories, since they are the most widely used unshaped refractories in industry.
Now let's take a closer look at castable refractories and how they are classified. The most important way to classify castables is by their bonding system, in other words, how the particles inside the castable are held together. Understanding the bonding system is crucial because it directly affects strength, temperature resistance, installation behavior, and overall performance. Broadly, castable refractories are divided into three main types based on their bonding mechanism.
The first category is hydraulically bonded castables. These castables contain cement, but do not use deflocculating agents. The strength development happens through a chemical reaction between cement and water, similar to ordinary concrete. While cement provides early strength and easy installation, high cement content can limit high-temperature performance. That's why the cement content in hydraulically bonded castables must be carefully controlled, especially for high-temperature applications. The second type is deflocculated castables, which are a more advanced form of hydraulically bonded systems. These castables contain cement and also include at least 2% by weight of ultrafine particles, typically around 1 micrometer in size. This deflocculating agents help disperse fine particles evenly and enhances flowability. As a result, deflocculated castables offer better mechanical strength and improved refractory performance compared to conventional hydraulically bonded castables. The third category is chemically bonded castables. These castables do not contain Portland cement. Instead, they rely on chemical bonding systems, such as phosphate bonds or sodium silicate bonds. By eliminating cement altogether, these castables avoid the thermal limitations associated with cement-based systems. Because of their bonding mechanism, chemically bonded castables are especially suitable for high-temperature and aggressive environments. Castable refractories can be further classified based on their density, and this classification plays a very important role in determining both thermal insulation performance and mechanical strength. Based on density, castable refractories are divided into two main categories. The first category is insulating castables. These materials have a bulk density of less than 1700 kilograms per cubic meter, which makes them lightweight compared to other castables. Because of their low density, insulating castables provide excellent thermal insulation. These castables are ideal for backup linings and insulation layers, where thermal efficiency is more important than mechanical strength. The second category is dense castables. These have a bulk density greater than 1700 kilograms per cubic meter, which makes them strong and durable. Dense castables are designed for demanding service conditions, where high mechanical loads are present, high operating temperatures are involved, and resistance to wear, impact, and chemical attack is required. Because of their high density, these castables provide excellent structural strength and long service life in aggressive environments. The choice between insulating and dense castables has a direct impact on equipment performance and operating cost. Insulating castables help save energy by reducing heat losses. Dense castables offer better protection, strength, and durability under severe conditions. In practice, both types are often used together. Insulating castables behind the lining and dense castables at the hot face. Insulating castables are lightweight refractory materials specially designed to reduce heat loss through furnace walls, while still helping the furnace maintain its required operating temperature. Because of their low density, these castables play a very important role in energy efficiency and overall furnace design. According to the ASTM C401 standard, insulating castables are classified into 9 different grades. Each grade is defined based on its bulk density and maximum temperature rating. Let's look at these grades step by step. Grade N, 55 pounds per cubic foot, rated up to 1700 degrees Fahrenheit. Grade O, 65 pounds per cubic foot, rated up to 1900 degrees Fahrenheit. Grade P, 75 pounds per cubic foot, rated up to 2100 degrees Fahrenheit. Grade Question 90 pounds per cubic foot, rated up to 2300 degrees Fahrenheit. Grade R, 95 pounds per cubic foot, rated up to 2500 degrees Fahrenheit. Grade S, 95 pounds per cubic foot, rated up to 2700 degrees Fahrenheit. Grade T, 100 pounds per cubic foot, rated up to 2900 degrees Fahrenheit. Grade U, 105 pounds per cubic foot, rated up to 3000 degrees Fahrenheit. Grade V, 105 pounds per cubic foot, rated up to 3200 degrees Fahrenheit. As you can see, higher grades generally have higher density and higher temperature capability. This means that when selecting an insulating castable, you must carefully match the grade to your operating temperature and insulation requirement. Choosing a grade that's too low can lead to failure, while choosing a higher grade than necessary can increase cost unnecessarily. In practice, insulating castables are most commonly used as backup insulation layers behind dense refractory linings and, increasingly, as primary linings in moderate temperature applications. They help reduce heat loss, improve energy efficiency, and lower overall operating costs. Now let's focus on dense castable refractories and how they are further classified. This classification is based on cement content, specifically the amount of calcium oxide. Based on calcium oxide content, dense castables are divided into four main categories. The first category is conventional castables. It contains more than 2.5% calcium oxide, which means they have high cement content. Because of this, they are easy to mix and install, cost-effective, and suitable for general applications. However, there's an important limitation. Portland cement becomes thermally unstable at high temperatures, so these castables are restricted to lower temperature applications. The second category is low cement castables. It contains between 1.0 and 2.5% calcium oxide. By reducing the cement content, their temperature capability increases while still maintaining good workability and strength. Low cement castables offer a balanced combination of performance and ease of installation. The third category is ultra-low cement castables. It contains only 0.2 to 1.0% calcium oxide. Strength in these materials comes from high-purity aggregates, optimized particle packing, and carefully controlled formulations. As a result, ultra-low cement castables can be used in very high temperature and severe service conditions. The fourth category is no cement castables. It contains less than 0.2% calcium oxide, and that small amount comes only as a natural impurity in the aggregates. No cement is intentionally added. Strength development occurs through alternative bonding mechanisms, such as chemical bonding, rather than cement hydration. Because of this, no cement castables offer the highest temperature capability and superior performance. When we talk about conventional dense castables, we are usually referring to materials with a calcium oxide content greater than 2.5%. To make selection easier, ASTM standards classify these conventional castables based on their maximum service temperature. In other words, how hot they can safely operate while still maintaining their key properties. According to ASTM, conventional castables are divided into 7 classes. Class A is rated for service up to 2000 degrees Fahrenheit. Class B goes up to 2300 degrees Fahrenheit. Class C is rated to 2500 degrees Fahrenheit. Class D can handle 2700 degrees Fahrenheit. Class E is good up to 2900 degrees Fahrenheit. Class F reach S3100 degrees Fahrenheit. And finally, Class G, the highest of this group, is rated to 3200 degrees Fahrenheit. Now, here's an important point to remember. These temperature ratings represent the maximum service temperature, not the temperature you should operate at continuously. As a best practice, you should always choose a castable with a temperature rating that's higher than your actual operating temperature. Typically, a safety margin of about 200 to 300 degrees Fahrenheit is recommended. This extra margin helps ensure long-term reliability, better performance, and reduced risk of premature failure. Now let's talk about erosion-resistant castable refractories and why they're so important in tough service conditions. Erosion-resistant castables are specialized refractories designed for areas exposed to fast-moving fluids or solid particles. Unlike conventional castables, these materials use extremely hard and dense aggregates, usually with high alumina content, to withstand abrasion and erosion. Common aggregate choices include tabular alumina and corundum, both forms of aluminum oxide. For even more severe conditions, materials like silicon carbide may be added. And in very demanding or specialized applications, you might even see exotic aggregates such as nitrides, tungsten carbide, or zirconia. Because of this composition, erosion-resistant castables are very dense. That density gives them excellent resistance to mechanical wear, but it also means they are poor insulators. And that's intentional. These refractories are not designed to keep heat in, they are designed to survive mechanical attack. Now, choosing the right erosion-resistant material isn't one size fits all. Selection depends on the exact nature of the erosion in your process. Key factors include the velocity of the fluid stream, the angle at which particles strike the refractory, the amount of solid particles being carried, and the type and hardness of those solids. Understanding these conditions helps ensure you select a castable that delivers long service life, reduced maintenance, and improved reliability in erosive environments. In short, when abrasion and erosion are the dominant failure mechanisms, erosion-resistant castables aren't optional, they're essential. Now let's look at how erosion resistance is classified and how these classifications help us choose the right refractory for the job. Erosion resistance is grouped into three main categories based on how much material is lost during standardized erosion testing. Simply put, the less material lost, the better the erosion resistance. First, moderate erosion resistance materials in this category show a volume loss of less than 20 cubic centimeters during testing. They're often used in areas with controlled velocities and relatively low solid loading. Second, extra erosion resistance here. The material loss is reduced even further, to less than 12 cubic centimeters. These materials offer significantly improved resistance and are commonly selected for demanding industrial applications. Third, extreme erosion resistance. This is the highest level of protection. Materials in this category show a volume loss of less than 4 cubic centimeters during testing. They are reserved for the most severe erosive environments, where particle impact is intense and continuous. Now let's look at moldable refractory materials and plastic ramming mixes. These represent a different approach to unshaped refractories. They are supplied either already moist and ready to use, or they need to be moistened before installation to get the right workable consistency. You can apply them directly as bulk material or in preformed cakes. The binder in these mixes can vary. It may be ceramic, chemical, mineral-based, organic mineral, or even purely organic, depending on the performance requirements. There are three main installation methods: manual ramming or compacting the material by hand using metal rammers; mechanical ramming, using pneumatic or powered rammers for faster, denser compaction; gunning, spraying the material onto the surface with specialized equipment. Once installed, these materials harden as the furnace heats up, developing their final strength and bonding. Moldable refractories and plastic ramming mixes are especially useful for patching damaged linings or in situations where casting or shaped bricks simply aren't practical. Now let's take a closer look at ceramic fiber materials, one of the most innovative developments in modern refractory technology. These fibers are mainly made from alumina and silica, formed into lightweight strands. To boost their performance, modern ceramic fibers are often enhanced with additives like zirconia, magnesium oxide, or yttrium oxide. These additives make the fibers much more resistant to high temperatures and reduce shrinkage. In fact, high-quality ceramic fibers can handle continuous service temperatures up to 1600 degrees Celsius. That's remarkable performance for such a lightweight material. Ceramic fibers have truly transformed furnace and refinery design. They allow thinner, lighter linings while still providing excellent insulation. Of course, like any material, ceramic fibers also have certain limitations. Understanding both their strengths and their limits is key to using them effectively in real-world applications. Ceramic fibers are manufactured in different forms to suit a wide range of applications. Let's go through the main ones. Blankets are flexible sheets of compressed ceramic fiber. These can be wrapped around furnace components, making them perfect for covering complex shapes or used as backup insulation. Modules are rigid, preformed blocks designed to fit specific furnace geometries. They make installation faster and ensure consistent performance. Boards are flat, rigid sheets of uniform thickness. These are ideal for lining flat surfaces or serving as thermal backing. Ropes, twisted or braided ceramic fiber used to seal gaps, joints, and doorways. They help prevent heat loss and stop gas from leaking in. Paper are thin sheets of ceramic fiber that provide a smooth facing surface, often used against equipment walls. Bulk fiber or loose ceramic fiber material, useful for packing, patching, or custom jobs where standard forms don't fit. The choice of form depends on the application, the geometry of the equipment, and how the insulation needs to be installed. The quality and performance of ceramic fiber materials depend on several key factors that manufacturers carefully control. Let's break them down one by one. First, short content. Shots are small, partially fused particles that form during fiber production. The fewer shots, the more true fiber you get, and that means better insulation. Premium grade fibers are designed to minimize short content. Second, fiber diameter. The thickness of each fiber affects both thermal conductivity and strength. Finer fibers usually provide better insulation. Third, fiber length. Longer fibers improve mechanical strength and packing density. The right balance of length ensures durability without compromising performance. Fourth, fiber orientation. How the fibers are arranged in the final product matters. Random orientation often gives more uniform properties in every direction. By understanding these quality factors, short content, diameter, length, and orientation, you can make sure the ceramic fiber you specify delivers the performance your application really needs. Ceramic fiber materials are classified based on how much heat they can handle. This is called the classification temperature, the maximum continuous operating temperature at which the material can still maintain its properties. The most common grades are grade 1260 degrees Celsius. This is the entry-level ceramic fiber. It works well for moderate temperature applications up to 1260 degrees Celsius. Grade 1425 degrees Celsius. This intermediate grade extends performance to higher temperatures while still offering good insulation. Grade 1600 degrees Celsius. This is the highest standard grade available. It can withstand continuous service up to 1600 degrees Celsius, thanks to advanced formulations and special additives. Mullite grade ceramic fiber, often considered the premium category. Mullite fibers have specialized properties and deliver exceptional performance, which we'll explore in detail next. By knowing these grades, you can match the right ceramic fiber to the temperature demands of your application. Now let's talk about mullite fiber, a specialized, premium category of ceramic fiber material with truly exceptional properties. Mullite fiber has a very fine, uniform microcrystal structure that is almost completely free of shots, those unwanted fused particles we discussed earlier. This refined structure gives mullite fiber outstanding thermal insulation compared to conventional ceramic fibers. Another unique advantage of mullite fiber is its versatility. It performs well in different furnace atmospheres, whether oxidizing, neutral, or reducing. That flexibility makes it especially valuable in applications where operating conditions can vary. Of course, These superior properties come at a higher cost. But in critical applications where performance and reliability matter most, the investment in mullite fiber is often well worth it. Ceramic fiber materials offer several big advantages that have made them very popular in modern refractory applications. Let's go through them step by step. First advantage: lower heat storage. Ceramic fibers don't hold as much heat as dense refractories. This means furnaces heat up faster and use less energy, leading to significant savings over time. Second advantage: shorter heat-up times. Because they store less heat, furnaces reach operating temperature much more quickly. For batch operations or frequent start-stops, this saves both time and energy. Third advantage: resistance to thermal shock. With low thermal conductivity and low heat capacity, ceramic fibers handle temperature changes with far less stress. This greatly extends the service life of the lining. Fourth advantage: lightweight construction. Ceramic fiber linings are much lighter than dense refractories. That means you can use simpler, less expensive support structures, reducing capital costs. Fifth advantage: easy repairability. If damage occurs, ceramic fiber can be patched or replaced quickly, often without long shutdowns. Maintenance is simple and reliability improves. Sixth advantage: thinner linings. Thanks to their excellent insulation, ceramic fibers achieve the same performance with much thinner linings. This gives you more usable furnace space and even faster heat-up times. All these advantages combine to make ceramic fiber an attractive choice for modern furnace design and operation. While ceramic fiber offers many advantages, it's equally important to understand its limitations. Let's go through them one by one. First limitation: velocity. Ceramic fibers can only handle a certain flue gas velocity. If the gas flow is too fast, the fibers may erode or get damaged. In such cases, erosion-resistant dense refractories are a better choice. Second limitation: low tensile strength. Individual ceramic fibers are not very strong. Blankets and modules provide reasonable strength overall, but they are not suitable for areas exposed to heavy mechanical impact or high loads. Third limitation: shrinkage. Over time, ceramic fibers shrink when exposed to high temperatures. This can create gaps in the lining, allowing hot gases to escape. Careful design and regular maintenance are needed to manage this. Fourth limitation: chemical attack. Ceramic fibers can deteriorate when exposed to certain chemicals like alkalis, sodium, vanadium, sulfur, or phosphorus from fuels. This reduces their insulation performance, especially in high-temperature zones. By keeping these limitations in mind, you can decide whether ceramic fiber is the right choice for your application, or whether dense refractories would be more suitable. Let's now look at backup insulation materials, focusing on calcium silicate blocks, one of the most widely used thermal insulation products in industry. Calcium silicate is a rigid, preformed insulation with very low thermal conductivity. In simple terms, it's an excellent insulator. It's also lightweight, with a density of around 250 kilograms per cubic meter. That makes it easy to handle and reduces the load on supporting structures. It offers moderate mechanical strength, so it can support loads and resist minor impacts. Another big advantage is safety. Calcium silicate is completely non-combustible, meaning it won't burn. It's also water-resistant, so it doesn't absorb moisture or lose performance when exposed to wet conditions. On top of that, calcium silicate can withstand high service temperatures, much higher than many other insulation materials. This makes it ideal for use as furnace backing insulation. When you combine all these properties, low thermal conductivity, lightweight, strength, non-flammability, water resistance, and high-temperature capability, it's easy to see why calcium silicate is the material of choice for backup insulation in most furnace applications. Calcium silicate insulation products are carefully designed with a specific composition to deliver reliable performance. At the core, they consist mainly of hydrated calcium silicate, a compound formed from calcium and silicon combined with water. To make the product stronger and more durable, non-asbestos mineral fibers are added for reinforcement. The manufacturing process is quite sophisticated. Under hydrothermal conditions, meaning high pressure and temperature with water, hydrated lime reacts with silicate to form a gel-like calcium silicate slurry. This slurry is the foundation of the product. Next, mineral fibers are mixed in to provide mechanical strength and impact resistance. The mixture is then shaped into blocks or pipe sections using a filtering press. The end result is a material that combines excellent insulation properties with solid structural strength, an ideal combination for demanding thermal insulation applications. Calcium silicate insulation products are standardized both in India and internationally to ensure consistent quality and performance. In India, there are two main grades. Indian Standard 8154. This grade is suitable for applications up to 650 degrees Celsius. It's typically used for moderate temperature insulation. Indian Standard 9428. This grade extends the limit to 950 degrees Celsius, making it suitable for high temperature furnace backing applications. Internationally, the standard is ASTM C533, which covers calcium silicate block and pipe insulation for use on surfaces up to 982 degrees Celsius. This aligns closely with the IS 9428 grade. These standards give engineers and technicians confidence that the material will perform as expected, making it easier to select the right grade for the job. Calcium silicate insulation is manufactured in two main forms, each designed for different applications. First form, block insulation. These are rectangular blocks, usually about 600 mm long and 300 mm wide, with thicknesses of 25, 50, 75, or 100 mm. Blocks are stacked and bonded together to form the insulation layer in furnaces. Their simple rectangular shape makes installation on flat surfaces efficient and cost-effective. Second form, pipe section insulation. For cylindrical equipment like vessels or pipes, calcium silicate is produced in curved sections that fit neatly around the pipe. This ensures tight insulation without gaps or wasted material. Pipe sections are available in a wide range of diameters, from small process pipes to large industrial ones, with standard fittings for easy installation. The choice between block and pipe insulation depends on the geometry of the equipment. Blocks are versatile and economical for furnace walls, while pipe sections are purpose-built for cylindrical applications. That brings us to the end of part 2 of episode 2 on the classification of refractory materials. In this session, we explored refractories based on their physical form, including unshaped refractories and related categories. Understanding these classifications is essential, whether you're designing new equipment or maintaining existing installations, because the right choice of material directly impacts performance, reliability, and efficiency. In the next part of this series, we'll continue with more classifications and dive deeper into specialized refractory materials. Thank you for joining me here on RefineryPro. Stay connected. The best is yet to come.